In this video, I'm going to be talking about how the nervous system deals with information. How does it transmit information from one place to another? This isn't about storing information, this is about how information is carried from one place to another in the central nervous system, or indeed in the peripheral nervous system. So my first question is, why does the nervous system use action potentials? As you probably know, most information is transmitted around the nervous system in terms of action potentials. And the idea is that the amplitude of these action potentials always stays the same, and that it's the frequency or the timing that contains the actual information, not the amplitude. Right, so it's a question of whether the action potentials are there, how fast they go, and what time they turn up. So why use action potentials? The reason is that if you've got a neuron with a long axon like this, if you have a graded potential, just membrane potential, what happens is if you stimulate here, you'll get a strong depolarization, but it will degrade very rapidly over time because the current spreads out of the neuron as it goes down, so it gets less and less as you go down. So that's no good if you want to send information a long way, because when you're picking up the signal here, so here you're trying to listen to the signal, you find it's very small, but you don't know whether it's small because the original stimulus was small or whether it's because you're such a long way away from the actual source of stimulation. With an action potential, once you've finally got one going, that action potential carries on all the way down and it gets to the other end completely undegraded. So this is to do with the issue of what we call fidelity. How trustworthy is the message? Has it run down? So that means if I have a high frequency here, I'll simply get an exact copy down here, and there's no problem of distance. If I have a low frequency, I'll get a low frequency here as well. So issues of fidelity. So that means then we store the information in terms of the frequency and the time that they turn up. But there's also another way that they do it, which is through labelled lines, which we'll come to in a minute. Right. So then that answers the question of why we use action potentials, and our answer is because of fidelity. It means we can signal over a large distance without things going wrong. Our next question is how is information encoded? And the simple answer to that, I guess, would be mostly with frequency. So the idea is that if you take a neuron and you poke it, right? So here's a neuron, and it wants to send a signal, and you give it a weak stimulus, you'll get a few action potentials going along at a low rate. And if you give it a strong stimulus, then you get a much higher frequency. So generally, what you find is if the intensity of the stimulus increases, the firing rate, so this isn't the speed of the action potentials, this is the number of action potentials per second. So don't get confused, it's not to do with the speed of the action potentials, that's constant. It increases, right? But it doesn't, just draw that slightly differently. So as I increase the firing rate, so as I increase the stimulus intensity, the firing rate goes up. So of course, at some point, there's some point below which we don't get any response at all. So that's 0. Because I can't keep going on forever, it flattens out. So we get this kind of sigmoid curve, and there's an area down here where there really is no encoding of the stimulus at all. It's just not responding. There's an area here where, again, we're not really saying very much, because no matter how much I change the intensity of the stimulus, the frequency doesn't change because I've maxed out. And there's this crucial area in between where I'm actually saying something useful, where as I vary the stimulus, the firing rate changes as well. So this is, if you like, our useful coding area. Now that means that I can't really, so say for example the stimulus might be light, it might be touch, or it could just be some presynaptic message that needs to be carried on. It could be force of contraction. So this is what we mean by encoding information. I'm representing the information, in this case the stimulus of some sort, by my firing rate. And the code is really simple. Bigger firing rate implies a bigger message of some sort. All right, so it could be, say, light or touch, or how much I want to contract, or a thought. It could be absolutely anything. So that's point number 1, is we encode information with our firing rate. But there's a bit of a problem here, because this means that if I want to have a very accurate representation of my intensity of my stimulus, I need this here to be steep. But the problem is, if I make this really steep, so a great thing about having a steep curve is that a small change in the stimulus is represented by a big change in the firing rate. So I've got a very accurate measurement, if you like. But the steeper I make it, the narrower this useful band gets. So the only way around that is to have neurons with different thresholds. So you end up covering the whole range by putting them all together. Right? So this is like a sort of a division of labour. But the other thing that we need to say is not just the firing rate, it's also which neurons are firing. So let's take a really silly example here. And so for example, I might have a neuron coming from my ear, and this one's firing away. So I know that because it's this one, it must be a sound. And if it's a low rate, it's a quiet sound. If it's a high rate, it's a noisy sound, it's a loud sound. If it's coming from my eye, then it must be light. Either an intense light or a low light. So if I'm sat inside my brain and I can't see I can't see any of this. All I see is these impulses coming in. I just need to know where they're coming from. So this is labelled as from eye. This is labelled as from ear. So this is why we call the labelled lines idea of information encoding. So it's where it's coming from. And of course, it's not just comparing eyes and ears. Even within the eye, if you like, we've got a retina, and where in the retina that this neuron is coming from is itself a labelled line and contains information. So where is the information? It's in which neurons are firing. That applies to here as well, and how fast they're firing. So to answer our question, how is information encoded, we have a combination of frequency and the labelled line. So I've answered two really important questions. Why do we use action potentials, and how do we actually represent information in the brain? I'm just going to add two more things now, just to complicate things just one little bit. And it's a couple of observations really. One, not all neurons have action potentials. That might come as a surprise. So for example, in the retina, there are lots of neurons which don't actually ever fire action potentials. If they're short enough, if they're small enough, then the amount at which the signal degrades is not significant because they're very short. So that might be one reason for that. So, and then related to that, and we're going to call this now point 1b, every neuron also uses analog signaling. Right? So they all use action potentials, which is digital, but they actually always use analog as well. What do I mean by that? So you might remember that a neuron has a cell body with its dendrites, but then it has a region called the spike initiation zone. Spike initiation zone. And that's where the action potentials start. So if you've got all these inputs coming in from other neurons like this, at this point we just have a spread of current coming in, making its way towards this area, and then it all adds up, and if it's above threshold, we get an action potential. So really, this area here is all analog, and it's only after here that it becomes digital. Right? So that's one thing to complicate things. The other thing is that, point number 2, is timing can also be used for information. The exact time at which a spike arrives can contain information. And this is often used in hearing to locate where a sound comes from. So what you do is you have a neuron coming from the left ear and a neuron coming from the right ear. And if the sound is coming from to the side, this action potential will arrive just before this one because it takes time for the sound to reach the right ear. So you actually end up with a slight delay, and that timing tells you the angle the sound is coming from. So then, that is our sketch of information coding in the nervous system.